Never be afraid. There's nothing which is known which can't be understood. And there's nothing which is understood which can't be explained. For over 50 episodes now, my team and I have brought you to the very frontier of knowledge in physics and astronomy. And still, our mission goes on. To present you with your birthright, an understanding of the universe. I've traveled the world seeking out a certain type of genius. Masters of not only their academic disciplines, but also at explaining their research in understandable ways. And I've bestowed upon these women and men the title of Titanium Physicist. You're listening to the Titanium Physicist podcast, and I'm Ben Tippett. And now, allez, physique! Let's talk about Annie Jump Cannon, an American astronomer who lived between 1863 to 1941, whose feats were as impressive as her name. This all has to do with stars. So consider stars. Some are bright and some are dim, and some are bright because they're close, and some are bright because they're emitting more light than normal. They're actually brighter. And some of them are different colors. Some of them are red, some are white, and some are blue, and some are yellow colored. Astronomers in the 1800s sorted out how to do spectroscopy, which is splitting up the light from a star into its rainbow of individual colors. And then based on the balance of colors, you can tell all sorts of things, like you can tell the temperature of the thing. The more blue light there is relative to the red light, the hotter the star is. And they also noticed and studied the absorption lines of the stars. So atoms in the atmosphere of the star absorb only a very specific frequency of light because of electrons jumping from one orbital to another. So if you look at the missing gaps in the star's rainbow, you can argue that these gaps are metaphorical bite marks and that the light has been eaten by specific chemical elements. So studying absorption lines tells you about the chemistry in the star's atmosphere. Okay. So it's the late 1800s and you're studying stars. Some of the stars are bright and big because they're massive and hot. Others are bright and big because they're old and running out of fuel. You don't know what the deal is. It's a big old mess. We need a way to sort out the stars into families that can let you process the difference between ones that are big because they're big and ones that are big because they're old. So in the 1890s, Harvard astronomer Edward Pickering was trying to take a photograph of every star in the sky. Part of the project involved obtaining a record of the optical spectrum of each star and then sorting them into categories. And now let's introduce Annie Jump Cannon. Miss Cannon was born in Delaware and got an undergraduate degree in physics and astronomy from Wellesley College in Massachusetts. At age 30, she got scarlet fever and then went deaf. And then, in 1894, she was hired as a physics instructor at Wellesley, and she took graduate-level courses at Wellesley and Radcliffe College, which is next to Harvard, which is why in 1896 she participated in Edward Pickering's cataloging project. The researchers were sorted into teams by gender. The men would run the telescope at night, and a team of women called the Harvard Computers would sort the stars and do calculations during the day. So you need to know that Annie Jump Cannon was really good at sorting the stars. She could look at one of these spectrum and recognize the slight differences in the emitted, absorbed black lines. And she was the fastest in the world at this. She was the fastest of all time. Over her lifetime, she classified 350,000 stars. Once she reached her stride, she could do 200 stars in an hour. But we'll get to what she's doing in a second. So the Harvard computers were debating how to sort these spectrums. They started by sorting it according to the darkness of the hydrogen absorption lines. They came up with a classification that started with A, which were dark hydrogen lines, and then B, less dark, and then C, D, E, all the way to Q. So this was a fine way to sort stars into categories, but it wasn't all that useful for telling you much about the star. So Annie Jump Cannon was like, hey, we should rearrange these according to the temperature of the star. Now, the basic idea is that there's only narrow temperature range where each element will absorb those particular frequencies. So depending on the temperature, some specific lines will be darker than at other temperatures. This new way of organizing rearranged the categories from A, B, C into a different order. Going from highest temperature to the lowest, the categories go O, B, A, F, G, K, M. O stars are the hottest. They're the blue giants, the heaviest stars that burn through their enormous fuel the fastest. And at the other end, M stars are the coolest. They're orange colored, and they're a fraction of the mass of the sun. Our sun, by the way, is a G-type star on the bottom side of the middle. So yeah, as I said, the classification of a star is by spectrum. You essentially look at this rainbow and locate which colors are missing, and then you choose the family based on that. And like I said, Annie Jump Cannon could look at this diagram and tell you exactly which category it was in. She could do 200 in an hour. It's absolutely bananas. Now, Annie Jump Cannon's lifelong astronomy career was notable and foundational to all of the amazing work that followed, theorizing and explaining what was inside stars, how stars worked, what they were made of. So she herself was a real superstar. And today on the Titanium Physicist podcast, we're talking about the brightest, hottest, heaviest stars in the universe, O-type stars. Speaking of superstars, our guest today has a list of notable creations as long as he is tall. He's just now completed his historic run on the Marvel Comics series, The Unbeatable Squirrel Girl, ending in episode number 50. Welcome back to the show, our old friend Ryan North.
Hello, thank you for having me.
Ryan, today, two amazing titanium physicists have decided to lend us their aid. Arise, Hannalore Gerling-Dunsmore.
Dun, dun, dun.
Hannalore got her bachelor's from the University of Maryland College Park and a master's degree from Caltech, and she's currently a doctoral student at the University of Colorado Boulder, where she studies black hole accretion disks. And arise, Benjamin Brown.
Do.
Dr. Brown got his PhD from the University of Colorado at Boulder, and then he did a postdoc at the University of Wisconsin-Madison, and then at the Kavli Institute of Theoretical Physics at UC Santa Barbara, and he's currently an assistant professor in the Department of Astrophysical and Planetary Sciences at the University of Colorado, Boulder, where he studies astrophysical fluid dynamics. All right, everybody, let's talk about O-type stars.
One of the things that I think is super cool about the story of Annie Jump Cannon there, before we go off on O-type stars, is just how amazing she was as a scientist. Because as you said correctly, she sorted all of the stars by their temperature, but she did not know, and no one else knew, that that was the way she was sorting them. She sorted them entirely on patterns that she could pick out in the data in front of her, and decided that this was a more sensible system of organization. This was in 1901, roughly, and it took actually about another 25 years until another woman in early astronomy, Cecilia Payne-Gaposchkin, came in and actually, in her doctoral thesis, applied the new ideas of ionization balances from Saha to derive the temperatures of the stars from their spectra and show that Annie Jump Cannon had sorted them by temperature. No one knew why Annie Jump Cannon's organization scheme worked so much better, and it took 25 years till someone was able to figure it out.
Yeah, and I think it's also really important to note that these were two women that were really, really influential astronomers around the turn of the century, which I feel like we hear a lot of people saying, oh, why do we care that much about diversity in science? Science has always been done by white men. Why do we need to change that now? And the reality is, no, that's not how it's always been done. There's always been women. There's always been people of color. There's always been disabled people. There's always been LGBTQ people. It's just that they don't get written into the history books. And so I think it's also really important to note that these two really influential women, and one of whom was a disabled woman who really just did incredible science back before people were really willing to write about them into the history books.
This was also at an era where the women in astronomy were not recognized as professionals in astronomy. Annie Jump Cannon was a computer at Harvard. It's Pickering who had all of the accolades and the professorial position. And women still found their ways to be involved in science and astronomy. It was often in these, call it the gig economy of the early 1900s, rather than full-fledged professional roles that we now think of as scientists being in.
Yeah, from my understanding, Cecilia Payne had to come from the UK because she wasn't allowed to actually study for a PhD in the UK. She had to come to the US to be able to do that. And even then, she still definitely faced a substantial amount of sexism. And I think that was part of the resistance to the conclusions of her thesis, which pointed out that the universe had vastly more hydrogen and helium than any other element.
She had been encouraged to pursue a career in music. The other cool thing, too, Ben, you were saying a little earlier that some stars are big and bright, and some of them are that because they're dying, and some of them because they're just hot. That actually we didn't know about at that time either. So this is 1901. Our observational tool for sorting stars is called the Hertzsprung-Russell diagram. To my memory, it was really sort of figured out in about 1910. So also about 10 years after Annie Jump Cannon was already empirically figuring out the right sort of organization and sorting of stars for their temperature properties. We didn't even have the real understanding of the temperature luminosity relationships that have led us to things like the main sequence and our understanding that big stars are bright and hot, low mass stars are small, dim, and cool, and so red in their color. So the work Annie Jump Cannon did was just truly amazing. It's a astonishing feat of human ingenuity with the empirical data that was available.
All right. So, Ryan.
Yes.
What do you know about stars?
Really put me on the spot here. I know that they're masses of plasma and gases that under the tremendous pressure of those gases, it ignites nuclear fusion, which is where higher elements come from. And if the sun disappeared, if all the stars disappeared, then we would all be dead.
Good. That's perfect. Good starting place. Okay, so the stars we're going to talk about today are on the extreme end of the spectrum. But the easiest way to explain it is in terms of introducing the ideas of sorting stars that we talked about in the introduction. Essentially, there's a whole bunch of different stars out there in the universe. Some of them are blue, some of them are orange, some of them are very bright, some of them are dim. What are you going to do? Hertzsprung and Russell, this diagram, what they did was they sorted all of the stars they could look at onto a chart where the bottom axis of the chart was in terms of color. So it was kind of Annie Jump Cannon's categories.
Right.
So red was on one side and then blue was on the other. It's one way of thinking about it is, I mean, you're sorting by color, but you're also kind of sorting by temperature because the hotter something is, the bluer it is.
Right.
And then vertically you sort them.
Wait, go back.
Yes.
You said the hotter something is, the bluer it is?
Yes. Well, I mean, if you have a lump of metal and you make it hot, you heat it up, it'll glow orange, right?
Yeah.
And you heat it up hotter, it'll glow red. And you heat it up even hotter, it'll start glowing kind of white.
Right.
Hot, it'll start to go blue.
Did not know that.
Yeah.
So blue hot is hotter than white hot.
Blue hot is hotter than white hot. Yeah.
I'm not sure the popular idioms have caught up with this knowledge.
Well, you don't want to touch anything that's white hot, even if it's cooler than something else.
Sure, but if you're like, baby, my love is blue hot, that's something to know.
There's a funny spot, Ryan, where it has kind of entered into popular knowledge, which is if you're ever buying LED lights at the hardware store and you're like, wait, I need to remember, my wife really wants it to be a nice warm light. I better buy the one with the cool color temperature. Right? So, well, at least in our case, you'll see they describe the color temperature of light bulbs in terms of some thousands of degrees. So 2700 Kelvin, 2700 K, this K is a Kelvin, degrees Kelvin. That's a kind of nice warm light, you might, have above your desk. And then there's the 5000 K, and that's a intensely kind of white bluish light that maybe you put in the hallways of the university here or something like that, but I don't want in my house on a day-to-day basis. Those temperatures are tapping into the same idea that when you heat objects up and they glow with light, the color they glow with and the brightness are both tied to that temperature.
That's great. And I feel like an idiot because I love that buying light bulbs now. There's like 3 metrics to keep track of, and it's more complicated
Right.
with LEDs. But I knew color temperature, and I thought, oh, it must be some metaphorical use of temperature because I recognize this K and it's Kelvin, but clearly the light bulb isn't getting up to 6,000 Kelvin. So I never made that last jump to blue being a metric of extreme heat, but I have now, and I'm excited to share this knowledge with the world.
Well, and
Yay.
the reason they use those temperatures is when we had the good old incandescent bulbs, they literally were heated to those sorts of temperatures to reach those different colors. Just to blow your mind even further, you, Ryan, right now are your own glowing, luminous being.
Get that all the time.
You probably are sitting at a temperature of about 310 degrees Kelvin, roughly. That means that you are glowing in the thermal infrared at about 10 microns, 14 microns wavelength. You're emitting infrared light right now. And if we could see you in infrared rather than visible, you would luminously glow.
That's oddly flattering. Thank
Isn't
you.
that cool?
I do feel like I have a sort of a glow today.
So you sort stars by temperature, but in this chart, but you also sort them by how bright they are. If you know how far a star is, you can measure how bright it is from Earth. Now, from Earth, it's kind of complicated because some stars are bright because they're bright, and other stars are bright because they're close to us, right? So you need to know how far away they are from us to correct for this. But once you have, you can put them on this chart. And you would expect it to be all random, that they would totally cover the chart. There'd be some that are bright and blue, and some that are bright and red, and some that are dim and blue, and some that are dim and red, and everywhere in between. But that's not what you see. Instead, it looks kind of like an archipelago of different islands where there's a long bean-shaped strip down the middle. We call that strip down the middle the main sequence. It's kind of a diagonal strip. And then there are little spots. So there's kind of one island called the Red Giant area, and then a blue giant area. Those are bright and blue. And then a white dwarf area. Those are kind of white colored and not very bright. And the deal is that there are not really many stars in between. And charting this out is actually really interesting because it means that there's probably something simple going on behind relating how bright something is and the color. And this kind of got connected to the life cycle of stars. It's called the life cycle, but essentially the deal, though, is that you don't usually get to see stars get old and change how they look. But what you can do is you can look at distant, they're called globular clusters, just like they're just a big, they're smaller than a galaxy, but it's a big collection of stars that formed way out past the edge of the galaxy. But you can kind of assume that this big group of stars all collapsed into stars from gas at around the same time. And then, you can't usually do that in the Milky Way because a group of a big cloud of gas will turn into a bunch of stars. And then as they orbit the Milky Way, they'll get kind of scattered everywhere. But if you look at these ones that are up above the galaxy, you can kind of say, okay, that family's probably been together since forever. And so you can say, okay, all of those stars have about the same age, and you can plot them on the intensity color diagram. And what it'll show you is kind of the evolution of stars, how stars over their lifetimes kind of go from one location to another. And this kind of puts into perspective why that some stars are bright because they're old. Essentially, a young group of stars won't have any of that type in it. But then over time, a population of stars that were all born around the same time, some of those stars will turn into big, bright red ones. And so these globular clusters, these little clouds of stars, it's essentially like a family photograph that was all taken at one time. And you can say, okay, so this is how these individual stars age, and this is how these individual stars age. And you can kind of imagine how they migrate around this diagram over time. And the deal is that all of the stars, really, really young stars, start out on that bean-shaped main sequence, that diagonal main sequence. And then over time, they move around. But most notably, it's the ones that are really bright and heavy that change first.
So the brighter ones last less time?
Yeah, the brighter ones last less time.
It's the Jimi Hendrix phenomenon.
Right.
It's like they say in Highlander.
It's better to burn out than fade away.
Yeah, that's it. So yeah, the stars that are brightest.
And so do we want to talk a little bit about why that is?
Well, I assume it's because they're burning more fuel.
So that's to first order, that's definitely it. Yeah. Exactly. Like they're larger, they're hotter, they have more pressure, they undergo fusion faster. And so they burn up their fuel. Just like if you had a small pile of wood and you put a bunch of maybe gasoline on it or something, and the fire is really hot, it's going to burn through that wood way faster than if you had a low smoldering fire going on.
That all makes sense. I'm glad that my intuitive Earth-based understanding also works for giant stars.
That's exactly how it works. Stars, like the sun, are bright because in the center of them, they're, like you said, fusing hydrogen. So, as we said, we figured out that the universe is full of hydrogen. These clouds of hydrogen collapse down, and then in the core of the stars, hydrogen atoms don't usually want to combine to make heavier things. But if you're in an area where there's lots and lots and lots of pressure and a really, really high temperature, and it's really hot in the middle of stars, pretty much because you have these big clouds of gas, they collapse under their own gravity, and so they heat up. And so the middle of them it's hot enough to fuse hydrogen, and doing so releases a little bit of energy, well, a lot of energy, and that energy is what heats the sun, and thus the Earth. And every star
on the main sequence, all of those ones on that beanstalk, they're all burning hydrogen in their cores and turning hydrogen into helium by taking effectively 4 hydrogen atoms through different nuclear processes and basically gluing them together to make helium atoms.
And releasing all this energy as they do so.
And one way I kind of visualize this is, again, going back to this fire metaphor. When you're burning a fire, it deposits an ash, right?
Yeah.
And so that's sort of the way that I use it to have an intuitive understanding of this process of taking these elements and producing another element out of their fusion.
Helium is the ash of the nuclear hydrogen fire.
Exactly.
Sure. It's a useful ash.
It's a very useful ash. And indeed, these subsequent and more massive stars, you're able to fuse higher and higher elements. And ultimately, we all exist because of these different ashes. So thanks, massive stars.
Yeah. Instead of we're all made of star stuff, it's we're all made of ash.
We're all made of star ash. That's right.
We're all made of star garbage.
You know, ashes to ashes, dust to dust is honestly a lot more literally true than you would naively think.
There's kind of an interesting aspect to this. It's like a fireplace. The hotter your fireplace is, the more fire there is, the faster that reaction can happen, and the faster you're going to burn out fuel. And it's kind of a runaway thing, right? If it's happening really fast, that will increase the temperature and it can happen much faster, right? So the deal is that on the lower mass stars, their interiors aren't very hot. And so this fusion reaction doesn't happen very quickly. But in the really, really heavy stars, yeah, the fusion reaction can happen much more quickly because it's heavy enough that it happens a lot, and then that releases even more heat, and so it happens even faster.
It's slightly more complicated than that, but not crazily so. So in the most of the stars have almost the same temperature in their centers because the nuclear reaction is so temperature dependent. That's a really good thermostat. If you change the star a little tiny bit, the nuclear reactions react a whole bunch. And they usually are a negative feedback. So whatever change you've made to the star, they counteract it and bring it back to where the star was.
Oh, it's like a self-regulating thing.
Yeah, it's self-regulating, right? So if I make the center of the star a little tiny bit cooler, then the nuclear reactions almost completely shut off. That means that the star collapses a little tiny bit, which heats up the inside, speeding the reactions up. Vice versa, if I heat the center up a little tiny bit, then the reactions become much, 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 much faster. And that means that the star actually can't really hold itself together and it poofs out a little tiny bit, which cools it down in the center, reversing the process. So they have a really good thermostat. And it means that the center of our sun's about 15 million degrees Kelvin. Mm-hmm. And it's really, really stable at that sort of temperature. The more massive stars are a bit hotter, but they're only hotter by a couple million Kelvin hotter than the center of the sun. And the very cool thing that happens there is that you actually get different nuclear reaction chains for burning hydrogen to helium.
What?
So,
Ben, that sounds like a really hot thing, not like a terribly cool thing.
It's super cool. So in chemistry classes back in high school or college, you might have learned about catalyzed reactions. which is where you like can do a reaction faster if you have some other thing to do it on.
Right, a catalyst.
A catalyst. The massive stars, especially the O and B stars, do a catalyzed nuclear reaction chain in their cores, where rather than just taking free-floating hydrogen and trying to like stick them together, which is hard, they use carbon, nitrogen, and oxygen, and they stick hydrogen atoms onto first carbon and then nitrogen and then oxygen, and then that oxygen decays, radioactively decays, spitting off a helium atom and returning back to the carbon. So they use this like crazy cool catalyzed reaction to burn their fuel faster and more efficiently, because they're just a little tiny bit hotter.
And that's what lets them reach the 3 million degrees higher temperature, is by using this different reaction.
They're at that 3 million degrees higher temperature or a few million degrees higher temperature because they're bigger. And that opens up this other...
that's what unlocks the reaction.
This unlocks the reaction. That's right.
Okay.
And that's one of the reasons that the biggest of these stars, of the O stars, can be 1 million times brighter than our sun.
Because they're doing a different reaction than our sun's doing.
Same reaction, but different...
catalyzed
different pathway.
Faster, better, stronger, harder version of it.
Yeah. They have the express lane. So.
All right. So, Ryan, there's one problem with our description. So far we're saying, okay.
I was about to say, I noticed there was one problem with your description.
Most stars live on this main sequence. So they're all kind of in a line. Bright blue stars are heavy. Dimmer red ones are light. And there's a continuum between them. And they're burning hydrogen.
Yeah.
So there's one problem with this, which is, here's the problem. In this picture, you only get that type of stars. What would a star do when it runs out of fuel? So the problem with this is you get a whole bunch of helium in the core, and then what? You run out of hydrogen and your star goes dark or something. But I've already told you that there's lots of, if you look at these diagrams of all the stars in our galaxy, there's more than one island on it. So some of the stars are off the main sequence. So clearly there's more to it than just it runs out of hydrogen.
Sure.
Okay. So the deal here is that you can fuse other elements besides hydrogen and release energy. You can fuse helium. Hydrogen fusion happens at about 15 million degrees Kelvin, right?
Right.
We just said that.
Yeah, I accept that.
Fusing 2 helium atoms, you need a temperature of 100 million degrees Kelvin.
So the heavier the elements you're fusing, the greater temperature you need.
Yeah, it takes more energy.
It's not just like a little bit more temperature. It's a lot more temperature to fuse these helium atoms.
Yep.
But there's a benefit. If you could fuse helium atoms, even though it happens at a much, much higher temperature, if you could, it releases more energy per atom.
To interrupt for a second, it doesn't actually. Hydrogen to helium fusion is like the most energy kick there is in the universe. But stars start relying on things like helium fusion because they've got nowhere else to go.
It's like when you eat all of your good snacks and you have to start eating those kind of trash snacks that you only bought because you went grocery shopping while hungry and they sounded kind of interesting, and then you got home and had a meal and realized, oh no, I've made a horrible mistake. That's a little bit.
This feels like a very personal story.
That's right. The hydrogen is the tastiest snack in the fusion chain. And then everything from there on out is diminishing returns and eventually a really bad bellyache for the star. So you do helium fusion, and you actually do a crazy thing. You do, rather than gluing 2 things together, you glue 3 things together all at once. We call it the triple alpha process. You take 3 heliums and glue them together and make carbon. And that gets you some energy. And then when you run out of helium and you have just carbon sitting around, now you start like gluing some helium onto the carbon, and you can kind of build your way up the element chain. And all is well and good until you get to iron.
I was going to say iron's the one where the energy it takes to fuse it is less than the energy it gives off during that.
That's right. That's right.
It's
Iron's like the tipping point. It's a tipping point in both directions, right? So if you have really big atoms and you split them apart, that releases energy. We call that fission, right? And that's what we do as humans here on Earth when we have like nuclear power plants. Gluing things together, releasing energy, that's fusion. And for both of those processes, Iron is at the spot where you don't get any energy by splitting it, and you don't get any energy by gluing things onto it. It's the bellyache at the end of all of the bad snacks.
But to be fair, not all stars get there. That's only really massive stars. Stars like our sun, they finish up at helium and then they get really, really big.
And they're done.
A lot of us have heard about, the sun eventually will expand and will consume the Earth. That's what's going to happen for these low mass stars. But as Ben Brown was saying, you have a really, really massive star. It's able to get hot enough and able to have enough pressure that you drive this fusion all the way down to iron. And you get this really dense iron core, which honestly, I feel like we all can relate to feeling like we have a dense iron core at the end of a snack binge.
And so a star like our sun, it makes a helium ash in the middle of it.
Right.
And then about 4.5 billion years from now, so a very long time from now, this happens. It runs out of fuel. It puffs up into a red giant, and it gently blows off its outer envelope, consuming the Earth and the interterrestrial planets in the process, and leaving behind this glowing ember of a white dwarf, of a probably helium white dwarf, that sits there slowly getting cool as time marches forward. The stars that are bigger than the sun by a bunch, especially getting up towards the O stars at the top of the main sequence, they're the ones that burn sort of one thing after another. And that's because they weigh more. So there's more mass. So they squeeze on themselves harder. So they get hotter in their centers. And so they can do these additional bits of burning. They can burn the ash and make a new ash.
Right. Right.
Kind of one after another. They actually have an onion structure to our understanding. So in the center, they're burning one thing. And then a little further out, they've gotten hot enough that they're burning some of their other stuff. Because a star like our sun only burns 5 or 10% of its mass. The rest is too cold, too far out in the star to ever catch on nuclear fire in a real sense. The massive stars, they have the fire in their center, but as they get hotter, there are sort of burning flame fronts of different nuclear reactions further and further out in their envelopes, converting more and more of their structure to interesting heavy elements, like all of the things that we and our planet are made up of.
That's super cool.
All the iron in your blood is just the result of a star's bellyache, which is either really awe-inspiring or really humbling. Maybe both.
So here's a question then. If at iron, that's where you get the bellyache and that's where the fusion stops, where do the elements heavier than iron come from?
That's a great question.
Ooh.
So there's a few different ways. So one of the ways, this is actually really, really recent that we had a detection of this, is a neutron star merger. So neutron stars are these stars made out of neutrons, this neutron plasma. They're super, super dense. They're the second densest thing in the universe besides black holes.
Right.
And actually, we're going to come back to neutron stars because, spoiler alert, after a star gets a really bad bellyache with all that iron in its core, one of the two options for it is to become a neutron star, and the other option is a black hole.
Right.
And so you can get two neutron stars that become gravitationally bound to each other, and they end up actually merging. And in those neutron star mergers, we get a good number of our elements heavier than iron.
Yeah, quick review of high school, nuclear physics. Elements are all separated they're classified by the number of protons and neutrons in their core, right? So how do you make something heavier than iron? You just pump more protons and neutrons into its core. Usually that doesn't happen. It usually takes quite a bit of energy to do so.
The word just there is doing a lot of heavy work.
Yeah. So in neutron star collisions, it just pushes out a huge spray of neutrons into space, which are then free to kind of stick together.
This requires two neutron stars to collide or interact.
Yes, to collide.
So do we see a drop down in the, population of these elements post-iron, where they're much more rare than everything up to iron because they're much more unlikely to come into existence?
That is a really good question.
Thanks. But I realize as I'm asking it, how would we count the number of, how do you measure that?
That's an awesome question. So one way is that, as Ben Tippett was saying in the introduction, is that you can look for things called absorption and emission lines.
Right.
And so you can actually tell what chemicals something is made up of in space by looking at what wavelengths of light are missing from the spectrum.
But that has to be something that's glowing, right?
No, because you can have light coming from all sorts of things that pass through other things.
Really?
Glowing with its own light or lit up by a different source.
Yes.
Yeah.
Huh.
So, for example, I study the accretion of supermassive black holes, and in particular with an eye towards active galactic nuclei, which are supermassive black holes at the center of galaxies, which are throwing off tons and tons of radiation through jets and other outflows. And so we get the radiation from these jets, and we actually see that all the way from so far away in the universe that the light has taken 12 billion years to reach us. And so those photons are lighting up stuff the whole way that they're coming along their path to us. And so we're able to tell the chemical composition of a lot of stuff due to that.
Well, hold on. Now I have another question. Because that's really cool. And it's my understanding that the observable universe is 13 and change, right? So that's coming a long way. But you maybe misunderstood. You were describing that photon as lighting things up along the way. But I thought a photon only lit something up if it hit it.
Well, it's passing through. It's interacting with it.
Oh, okay. Passing through semi-transparent things.
Yes. And that's
Yeah, okay, that makes sense.
Yeah, and we're actually going to talk a little bit about opacity later on. So this is a great time to introduce this concept where there's this idea that we're used to in our day-to-day life. If you have a window, light comes through it. In fact, most of the light comes through it. And then you can put maybe fabric or a tinting or something over a window, and that lowers how much light comes through it. And then you have something like a wall, and no light comes through that.
Mm-hmm.
So a wall is really, really opaque, meaning that radiation and light light is a type of radiation, but so radiation doesn't pass through it, whereas something that is a really low opacity means that a lot of the radiation comes through it. And so a lot of the matter in the universe has fairly low opacity.
Huh.
So windows let light through, right? So that we can see.
Yeah.
But they do something else. At least if you're like me and you live somewhere that has winter, you have windows that have insulation in them.
Mm-hmm.
So they let visible light through, but they don't let heat through. They don't let infrared light go through. So they're transparent to visible light for modern windows, but typically are either reflective if you're in a desert climate or insulating if you're in a mountain climate to try and trap the infrared light inside the house rather than just letting the infrared light from the heat of the house flow out through the window. So that's one of these ideas where one kind of light might be able to go through something, but a different kind of light might be stopped by the thing. It might be transparent to one and opaque to the other.
That's a great explanation, especially since I had not realized. I know that you want a window that keeps the heat in. I live in Canada, but I hadn't realized, you're just making it opaque to or reflective to infrared and transparent to visible. That's neat.
That's right. You're creating a little tiny greenhouse effect inside your house through your windows.
That's cool.
Okay, so in addition to these neutron star mergers, which I find really exciting because I love compact objects. So those are things that have significant relativistic effects to the gravity surrounding them. So that's why I bring those up. And actually, we were able to detect neutron star mergers through gravitational waves, in particular using the observatory LIGO, which you might have heard about the first LIGO detections a few years ago, which Kip Thorne and I forget who else, but there was a Nobel Prize awarded for the prediction of gravitational waves now that they were detected. It's a huge deal. So it's very exciting. But also very exciting is another channel of nucleosynthesis is actually in the supernova that happen after these massive stars die. So as we were talking about, these massive stars develop a shell structure due to this deposit of quote-unquote ash through fusion. And Titanium Physicist already has a core collapse episode, so I'm not going to go into too much detail, but basically, eventually there's so much mass that the electron degeneracy pressure can't support the core collapses, hence the name. Then eventually the nuclear force becomes repulsive, that's how dense it gets, and it causes the core to bounce and send a shock moving outwards.
Right.
Okay, great. So the shock's moving outwards, but stars are really, really big. And so there's a lot of matter from the outer layers of the star that are still falling inwards when the core bounces. And so you have this infalling shock from the outer layers, and then you have an outgoing shock from the bounced core.
Right.
And eventually they run up against each other. So we actually currently don't know exactly how these shocks get revived and result in a big explosion. But one way that we think is that there's a bunch of neutrinos, and essentially the matter boils on the inside shock and gives enough energy to blow out the infalling outer layers. And part of that is there's a ton of energy going around, and part of that is how some of that energy goes into making elements heavier than iron. So that's pretty cool. Ben Brown, do you want to add anything to that?
Well, I was actually stuck on an image I wanted to share, which is this image of the core starting to collapse and then the rest of the star kind of reacting afterwards. I think of it as like the Wile E. Coyote moment in a star's life, because the iron core, when it starts to collapse, it collapses faster than the speed of sound in the plasma of the star. Right. It happens really fast. It happens on a free fall. And for material fluid objects like stars, fluid dynamics tells us that the way that you communicate mechanical changes, that happens with pressure waves, with sound waves. So in a real sense, the floor falls out from underneath the rest of the star faster than the speed of sound. And so the rest of the star is just like, hey, where'd the floor go? And about when it says that is when the center has like collapsed down to a compact object, done whatever the heck's going on there, rebounded, and then sent a shock wave blasting outwards. So right when the rest of the star is like, hey, the floor just left.
That's when
maybe we should start falling too. And it's doing the Wile E. Coyote, like legs spinning in space. That's when suddenly this blast wave rips through it from the interior of the star. So
that's awesome. That's the most metal.
That's about what I've got.
Yeah, well, I mean, honestly, it's all metals besides the hydrogen and helium.
In astronomer speak, at least. That's right. Anything heavier than hydrogen or helium, it's a metal.
That's true. Yeah. And I'm sure that it just drives chemists absolutely up the wall to hear us saying that.
So, like, this is the mechanism driving supernova. That's when the thing explodes and becomes the brightest thing in the galaxy, right?
That's right.
You could see, you can't differentiate between individual stars in a distant galaxy, but you can see a supernova when it happens, even from halfway across space.
A lot of these supernovae are happening in these O stars. So the stars more massive than the sun are the ones that can start to go down this road. And they're the B stars, which are kind of like, I don't know, 5 to 15 times the mass of the sun. And the O stars are kind of like 15 and above. It's an all of the above kind of thing. So it's all the really big stuff. And like what happens to a B star is complicated because you need enough mass to trigger some of these nuclear reactions from being heavy enough to be hot enough. But at the same time that all this stuff's happening in the core, like the outer envelope is heating up and getting blown off. Like there's all sorts of dynamics in the outside that's stripping mass away with the winds. And the O stars just have a lot more mass to begin with. So you're a lot more likely to have enough around at the end of the day to trigger a supernova explosion by pushing you to like this silicon burning to iron kind of regime than the lower mass stars. So a lot of the supernovas are coming from the upper end of the HR diagram, and they're brighter than whole galaxies when they happen. So we see them from across the universe. We see thousands a night in surveys.
Sorry, you said we see thousands a night?
I think that's right. We either do now or we will when the large-scale synoptic telescope that's being built down in Chile starts mapping the entire southern sky roughly once every 2 weeks. So,
wow.
They're
I had no idea they were so frequent. I guess that's where you're making all these heavy elements from. You'd need them to be that frequent.
That's right. They're frequent also partly because this is where all the heavy elements come from, right? And by heavy, we mean anything other than helium. These O stars don't live for very long. Like they have lifetimes of like tens of millions of years rather than like our sun, 10 billion years. These things live for 1,000th that time. We've had 6 or so generations of some of these just since the dinosaurs were wiped out by an asteroid impact.
So correct me if I'm wrong, but my sort of impression, naive understanding, is that as time goes on, fewer and fewer stars are being formed because we're using up all these collections of gas. So would we reach, I guess we would reach a point where there'd be no more of these O-class stars because there's no large enough collections of gas to form them, right?
Maybe in a very, 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 very long time.
Oh yeah, like cosmic, like life of the universe stage stuff. And my question sort of leading to is like, is there a way we could tell where we are in the universe's life cycle by how many of these stars there are?
Kind of. So very early on, the very first stars that were formed, we think, the first generation of stars, those are thought to have been much larger than any stars we form today. So like many hundreds to maybe even many thousands of times the mass of the sun. Those like almost aren't even stars. They're kind of like events.
Right.
Because like almost as soon as like the mass starts collapsing in and fusing, it already is like falling apart and blasting itself outwards. They're kind of crazy objects. But they're the ones you can form when you don't have any elements other than hydrogen and helium and other Big Bang elements. So you can't kind of break the gas up into chunks and cool it off.
Frustratingly, those are called population 3 stars, despite being the first generation of stars, because astronomy nomenclature doesn't have to make sense. It's astronomy.
That's right. Modern stars that are forming now are pop 1 stars. The very first stars to form were pop 3 stars, even though 3 comes before 1 in this counting. And there's nothing after 1 to talk about like what's going to be the long run changes. But the thing to remember is that even with these stories of like nuclear fusion and like successive burning of elements and supernova explosions, and even in the massive stars where like a lot of burning can happen, you're still only burning a fraction of the total mass of that star. So you might only be burning 10% or maybe 20% of the total mass of that star. The other 80% stays as undisturbed hydrogen and helium that's part of the star and then gets blown back out into space, turns into another gas cloud somewhere, gets recycled into another star. 10% of that burns, gets blown back out into space. And so there's a lot of recycling going on too.
Yeah, I didn't realize that. That makes sense.
So Ryan, to get back to your question, I'm not sure how much we could really say about the universe's life cycle, but we absolutely can say something about a local region's life cycle by looking at what kind of stars are there. And so in older regions, you aren't forming stars. You have, a lot more larger scale structure that's developed, and it doesn't have as much of this stellar formation going on. And that's especially something that we use to talk about what's going on with galaxies and where they are in their evolution as we look at the or what would have been the star forming regions at the interior of galaxies. So while I wouldn't say it's necessarily something we can use, at least not yet, on a cosmic scale, we absolutely use it on a local scale.
That's super satisfying to know.
To add another point to that, I mentioned globular clusters, just these big clouds of stars that are, it's a group of stars, thousands or hundreds of thousands of stars that they're kind of orbiting as a collection, the Milky Way. So one thing we can do is look at something called the metallicity of the star, which tells you how many heavier elements there are in it, heavier than helium. If it has low metallicity, if your population of stars has low metallicity, it means it's really old, because the stars, say, in the Milky Way have so many of these heavy elements because they've been through so many of these cycles of supernovas that it kind of changes the overall chemical composition of the stars that are next to form. So you can look at the presence of these heavier elements as an indicator of how old that particular cluster is. If it's got lots of the heavier elements, it means that it's newer. And if it's got few heavy elements in it, if these stars have fewer of these heavier elements in their atmospheres, you know that this population is really, really old. And so with that knowledge, you can kind of date specific, say, globular clusters or clusters of stars. And with that knowledge, to see and date essentially, hey, when do these O-type stars blow up? How old do they get? That's kind of the fact that we can take a snapshot of a cluster of stars, date it based on the metallicity, helps us interpret, that these O-type stars go poof, in a matter of millions of years instead of
and
billions.
also makes sense. So two pluses.
So here's the thing, though, is O stars aren't just interesting when they die. Their very, very short lives are also super, super fascinating.
Go on.
So maybe we should pause for a second before we go into the world of O stars to give you kind of an idea of stars more generally along this main sequence, maybe starting with our sun, so that some of the things that are very cool about O stars make some sense about why they're so cool. So our sun's what we call a G-type star. Astronomers were creative in our measurement system, so it's one solar luminosity and it's one solar mass. It lives for about 10 billion years. The center is a nuclear fusion region, and is in the center of the sun for the inner about 2/3 of the sun, the inner 70% of the sun by radius. The energy that's created by the nuclear fusion is carried outwards by light, by photons. It's all opaque to the photons, but they carry all of the energy. And so the plasma that's down there is what we call stably stratified. It probably doesn't move a whole lot. It just kind of sits there as the light kind of goes through it. It takes quite a while for the light to get through. It takes about 1 million years for a photon that's created in the center of the sun to sort of trickle its way out by radiative interactions through the interior.
Is that because of gravity?
No. Oh, it's because the inside is opaque. And so the photon doesn't get very far. It's flying along through the inside of the sun, and it runs into something and gets absorbed. And then that thing emits it again, and it flies along, and the distance it's going are very, very, very small. And it kind of goes in random directions after each absorption and re-emission. So it kind of random walks and diffuses its way outwards from the center.
Okay.
It's kind of working its way through a fog.
Right.
So it's a little bit...
Yeah, go ahead.
So it's a little bit like, imagine you have a sort of narrow hallway and you like throw a ping pong ball against one wall. The more bounces that ping pong ball has, the more energy it loses, and the shorter the distance down the hallway it's going to end up making it.
And I've got to get it all the way down the hall for it to escape.
Exactly.
That's right.
Yeah. Okay, that makes sense.
So, but it's the sun, and so 2/3 of the way down the hall, things suddenly change. So the sun, as you go from the inside to the outside, it gets cooler and cooler. You start at about 15 million degrees at the core, and the photosphere, the sort of surface of the sun, is about 6,000 degrees. So you change in temperature a lot. Hot in the center, cool at the outside.
Is there a surface, or does it sort of just diffuse?
No. Yeah. There's not a surface. So what we call the photosphere, it's basically where the sun goes from being opaque to transparent, but it does it in kind of a fuzzy, gradual way, but it also happens over like 100 kilometers of distance. And the sun is like, let's see if I can do it in kilometers. It's 700 megameters. That's like 700,000 kilometers in radius. So it's fuzzy at the edges, but that fuzziness is not very much compared to the size of the sun itself.
Right. So it feels, we can conceive of it like a surface because it's so thin compared to the rest of it, but it's not.
That's right. If you stood on it, you would not be able, there's nothing you could stand on, right? Aside from the fact that you'd, crisp and then melt.
There'd be no clear defining line between space and sun.
There's no clear defining line between space and sun.
Right.
And in fact, the sun extends all the way out in some senses, out to the earth and beyond in the wind that we're embedded in from the sun.
Right.
But
at that point, we sort of have to question what we mean by sun.
That's right. So as the photons are coming out from the sun, about 2/3 of the way out, about 70% of the way out, the sun now gets cold enough that it gets even more opaque. And it gets opaque enough that it starts to really absorb the photons and not just re-emit them. And this completely changes the structure of the sun. The photons no longer carry the heat, and the plasma of the sun itself starts to, in some senses, churn and almost boil. And the plasma now, the physical material of the sun, it starts to do what we call convect, and it gets hot and it rises upwards towards the faraway surface, where it cools down and then falls back down within this region. We call it the convection zone of the sun.
Okay.
So the outer third of the sun is full of churning large-scale plasma motions of convection. The inner two-thirds are sort of slow, gentle radiative diffusion. We call the inside the radiative zone. We call the outside the convection zone. Convection zone says all sorts of cool things. It's where the magnetic field of the sun is generated. It's where the dynamo of the sun operates. Dynamo is a fancy word for saying plasma motions turn into magnetic field. Sunspots are generated by that. The 11-year solar cycle comes from that. All sorts of crazy things happen. And the very surface of the sun, since it is effectively the top of the convection zone, the surface of the sun is very complicated. And if we look at it with good telescopes, like the Big Bear Solar Observatory in Southern California, or the DKIS telescope that's being built in Maui right now, and we'll start doing observations of the sun in about a year's time, we can see patterns on the surface that are bubbles of convection that turn over about every 5 minutes, that are about the size of either Texas or France, that are constantly churning and breaking apart and bubbling away.
If you look at a photo of the sun zoomed in, it's like, you know what a sunspot is? That's a big black spot, right? We're not talking about that. We're talking about, like, if you look around anywhere else on the sun, it's still really patchy. There are spots that are bright yellow and in these photographs, and spots that are like orangey. It looks like a giraffe.
Yeah, it's the giraffe pattern. It's the giraffe pattern around the sunspots.
Have you ever seen?
Yeah, I look at the sun and I think that's
right.
Yeah,
basically.
So what these photographs are is, I mean, hot things glow more brightly than cool things. That's basically what's happening. The convection bubbles that are erupting and letting off their energy into space at the top of the convection zone, those are the bright spots. And then where the plasma is sinking down to replace it on these conveyor belts, those are kind of the darker spots because the plasma is cooled. And so when we look at the sun through the photo to the you know, the top of the convection zone, the part that we see when we take these photographs, that splotchy thing is really this convection process, bringing heat from the middle of the sun out into space.
That's right.
That's cool.
And the sunspots are about the size of the Earth, roughly. The splotchy pattern is about the size of, like, France or Texas, like I said. So the splotchy pattern is small compared to the sunspots, and it is visible essentially everywhere. And that splotchy pattern changes every 5 minutes. The surface of the sun's even more complicated because you not only have this splotchy convection that's churning away, you also have magnetic fields all over the place. So you have the big magnetic fields of the sunspot regions. So the sunspot regions are regions of about a kilogauss of magnetic field. That's pretty strong. That's like approaching if I remember right, that's kind of on the same scale as like the magnetic field in an MRI machine.
Okay.
And that magnetic field is so strong that it actually can stop the splotchy convection of the sun from bringing heat up from the interior, just very near the surface layers here. And so those regions don't have enough heat coming up, and so they get cool. And since they're cool, like we were talking about earlier, cool things are dark, hot things are bright. So the sunspots are cool, and that's why they're dark.
So I think this might be an open question, but do we know what causes that magnetic field in the sun? Where it comes from?
No, we really
crazy.
don't. And part of my day job is to study where those sunspots come from, and we really don't understand where they come from other than inside the convection region of the sun. And we have some different theories, and they have their pros and cons, but it's really not something we have an answer to.
That it's such a, the sun's so huge, and we're not quite sure where this stuff is coming from. There's still...
We really don't know. And we profoundly care, because on the one hand, the sunspots have all of these just amazing patterns to them. So that you see certain patterns come up over and over again an organization of these sunspots. They're in the middle of this like crazy turbulent convection zone where you think there'd be like no rhyme or reason or anything, but they have like all these simple rules they by and large follow. They're tilted at particular angles. The sunspot in the front has one magnetic polarity compared to the one behind it. That changes across the equator between the north hemisphere and the southern hemisphere. They follow 11-year cycles that are linked also to the north-south field of the sun reversing. There's all of this just clear and beautiful patterning. And, we don't know, like, are they formed at the bottom of the convection zone of the sun? Are they formed in the middle of it? Are they formed near the surface? The other reason we care about it intensely is that these sunspots are where the sun has flares and plasma storms that come out and hit the Earth. And those, like, this is one of these few cases where an astrophysical object actually can affect day-to-day life down on the surface of the Earth, for power grids, for long-distance flights, for communications networks.
It'd be nice if we could predict that.
Be nice if we could predict that. And we have been observing the sunspots in detail since the time of Galileo. So we have like 400 years of observational evidence of these sunspots, and we're still trying to figure this problem out.
That's so cool.
Isn't that cool?
Yeah.
Shoot. Okay, when we said the source of sunspots was mysterious, I want to just kind of put an asterisk next to that, because it's not like we think that it's aliens doing
If
it.
I can interject there.
We have a
Definitely
good sense of why, but not what starts it. Do you want to just go crazy, Hannalore?
Do I?
Talk about it?
Do I want to talk about
Yeah.
aliens? No, I don't want to talk about aliens.
You want to talk about
The real
magnetohydrodynamics.
Oh, right. Okay. Magnetohydrodynamics. Sorry. I got like really hung up on like my stupid little quip about aliens. And I'm like, no, that was just a dumb throwaway joke. Oh, okay. So magnetohydrodynamics basically is actually encapsulated in the name, where it's this study of fluids that are magnetized. So people are generally familiar with the stages of matter being solid, liquid, and gas, with them being listed in increasing order of energy and separation between molecules. So going beyond gas, we have plasma, where in plasmas, the electrons have been ripped off of off of molecules, and that become ionized. And so there's a charge separation. And as a result, we have this fluid that interacts with magnetic fields. And fluid dynamics on their own are really complicated and really hard. And when you bring in magnetic fields, it only gets more complicated and more confusing and more difficult. And so that's introduction to MHD.
So right, it's not just aliens, and we actually have very sophisticated theories, understandings, and models for how the fluid dynamics of the convection in the inside of the sun, which is powered by the heat of the sun and the need to transport that heat outwards, how the convection interacts with the rotation of the sun and the magnetism, and through MHD, magnetohydrodynamical processes, you can take the convection that's driven and powered by the heat and convert that energy into magnetic fields by stretching and amplifying and creating them. And these can create both sort of small scale magnetic fields, like we can see scattered across the parts of the sun that aren't the sunspots. And they can also create very large scale magnetic fields. And part of the way that you get that is when you have very large scale flows in the sun, some of which we observe. Those large scale flows can organize and amplify those magnetic fields. So we tend to study these using numerical tools, computer simulations, to solve the math equations of magnetohydrodynamics and to do them in sort of cartoon models of the sun. And we've been doing this in a pretty major way since sort of the early 2000s. I actually did my PhD thesis on these sorts of problems. And so I've seen this field from sort of where it was sort of really taking off in the early 2000s all the way through to the modern era.
So one of these processes that Ben Brown mentioned earlier is the dynamo, which, well, I think a lot of people have heard of Maxwell's equations, right?
Yeah.
Yeah, okay. So there's two equations in Maxwell's equations called Faraday's law and Ampere's law. And those two laws basically say that a changing electric field can create a magnetic field, and a changing magnetic field can create an electric field.
Yes.
Well, a displacement current. Anyway, so what happens with a dynamo in a plasma is that you start off with this weak magnetic field, and that sloshes or moves around. It changes a little bit, and you get an electric field from that. Now you have this electric field that starts changing because the B field that made it is changing. That's right. You get another magnetic field coming from that changing electric field. And in this way, you end up getting what can be thought of a little bit as a runaway effect to build up a really substantial magnetic field from what was a really small magnetic field. And that's, again, called the dynamo process.
To bring it back to the sun, the deal is that or charged particles, they can travel along magnetic field lines without feeling any force. But if they try to travel perpendicular to a magnetic field line, they'll feel force trying to spin it in a little circle. And so the consequence is plasma is made of nothing but charged particles. The plasma can move in the direction of the magnetic field line, but can't move perpendicular to it. And so there's this really weird interplay between how the plasma is moving and what the magnetic field is doing inside the sun. Because of this convection bringing plasma in and out of the sun, and because the sun is also a big ball of rotating gas, one way to think about magnetic fields is like a little rubber band, right?
Right.
Rubber bands are loops, and you can't, you can bend a rubber band, but you can't change how it's connected. So one way to imagine this is you have all this churning gas in the sun, this churning plasma, and it might have one of these magnetic field rubber bands in it. That rubber band, as the gas goes up and down and swirls around in different ways, is going to get twisted and twisted and twisted on the inside of the convection zone. And this is the big mysterious part that Ben was talking about, where we're like, we don't quite know what happens. Nobody's quite sure how this works, but the magnetic field rubber band, it gets twisted around so much that a little ring of magnetic field breaks off and becomes disconnected from the rest. And somehow that we don't know where it happens. The details are still out, but that's the mystery part of the mysterious. What we know then is that little ring of magnetic field line will slowly rise to the surface. And as it punches through the surface, what we see is magnetic field coming out of the surface somewhere and then looping back down around and going back into the surface. Because what we're seeing is the magnetic field line puncturing the surface. And because it's a ring shape, it's going to puncture it in two places.
Right. Does that happen in any other circumstances? Like, do we know of that happening in other circumstances, a magnetic field getting twisted and spinning off a tinier magnetic field?
So that's a process called reconnection. And in reconnection, you actually get a huge amount of energy because these magnetic fields are sort of brought together and then snap apart. A rubber band is a really good analogy for them. And we see reconnection, or we think we see reconnection in a variety of places. We see it in tokamaks, where there's nuclear fusion. We see it in black hole accretionists. We see this in a lot of areas where we have these plasma flows. Absolutely.
We see it also in the Earth's magnetosphere, and it's one of the reasons that we get things like northern lights and other interactions with storms from the sun. And it's something that is in plasma physics is studied in laboratories a lot. So Madison, Wisconsin has a vibrant plasma physics community working on problems like reconnection. It's partly because of what Hannalore said about tokamaks. It happens in the devices we are trying to build to make nuclear fusion a functional power source for here on Earth.
That's cool. Did not know that.
So what makes fusion really, really hard here on Earth in tokamaks is keeping the plasma confined, because if it touches the walls of the reactor, it cools off and stops fusing. So part of why reconnection is so important for us to understand is that, as I said, you get this kind of snapping effect that releases a lot of energy and makes the plasma harder to confine and harder to keep where you need it to be.
So to put a cap on the sunspot description, this reconnection somehow happens inside the sun, and you get this ring of magnetic field that pops up through the sun. Where the two magnetic fields pass through the sun, that's the dark spots that we see as sunspots. So sunspots are always going to occur in pairs because they're always going to form when these rings of magnetic field pop out. And it's also attached to the have you ever heard of a coronal mass ejection?
Yes, I've heard of it, but I'm not sure I could. It's just like charged particles coming out of the sun, right?
Yeah, well, what these photos look like is there's like a photo of the sun sometimes from the side, and there's a big fiery, it looks like a fox's tail,
real?
a big fiery thing of plasma stretching out. What's that?
Oh, wow.
Yeah. In fact, they come out of the sunspots. They don't quite come out of the sunspots, but the plasma in the sun can pass along the magnetic field lines. They just can't pass through them. And so the charged particles ride up the magnetic field lines, and then as the bubble of magnetic field passes up through the surface and out into space, this arm full of plasma spews off into space. So these two seemingly unconnected, the coronal mass ejections and the sunspots, are actually explained in terms of there's a ring of magnetic field lines, a hoop of magnetic field lines that are passing up through the surface of the sun and bubbling out into space.
So there's always an even number of sunspots on the sun.
Yeah, exactly.
More or less.
More or less? What's that asterisk mean?
What that asterisk means is that sometimes the ring doesn't come down in a neat other spot. So sometimes you have a couple of these rings clustered together into what we call like a delta formation of sunspots. It looks like kind of a little wedge with like some trailing stuff behind it. So you have a couple of these like cross-linked with each other and all mixed up. That's where you tend to get more of these flares and storms out of. Sometimes the ring also comes down rather than in an organized spot. Sometimes you can get a single isolated sunspot because its magnetic fields, rather than all coming down at one other point that makes a spot, they come down diffusely, sort of scattered all over the place for reasons we don't really understand. And that actually leads to other cool changes. So when the magnetic field on the sun is very concentrated, it's dark because it stops the convection from bringing heat up.
Right.
When the magnetic field is loose and scattered, it's actually bright. And the reason for that is when you have a magnetic field in a plasma, the magnetic field has some energy to it and a pressure to it. And that means that the part of the plasma that has a little bit of magnetic field has a little bit of extra pressure compared to plasma near it that has less magnetic field. And so if those two balance in pressure with each other, the way that balance comes about is that where the magnetic field is, there's a little bit less plasma in that spot. So when you look at the spots that have a weak magnetic field on the sun, diffuse magnetic field, you can actually, there's a little bit less gas there at the surface. You can see a little bit deeper into the sun where it's hotter and brighter.
Oh, cool.
When they were first found, these regions were called plage, which is the French word for beach, because it looked like beaches on the surface of the sun.
I love that there's these big open questions still left to figure out. For something that seems so bright, obvious as the sun, there's all these questions left with it.
Our simple neighbor star.
We know, so from my understanding, we don't know very much about the sun. We don't know very much about things in space. That's why it's so fun to study. It's so exciting.
On the one hand, we don't know much about the sun. On the other hand, we have a science called helioseismology that lets us measure properties of the interior of the sun to better than 1%.
Wow.
And we know the interior of the sun so well that there was a huge problem in science, especially in kind of the 90s and early 2000s called the solar neutrino problem, where particle physics made one prediction for how many neutrinos we should see coming from the sun from nuclear fission at the core. And our understanding of solar structure based on stellar structure models in astrophysics and helioseismology observations of the sun made a different prediction. And the only way to reconcile the two was either that the inside of the sun was completely different than we thought, or particle physics worked completely differently than we thought. And the resolution was that particle physics works completely differently than we thought for neutrinos, which is just sort of one of the more profound triumphs of solar and stellar physics.
Yeah, he won that fight.
Okay, stars that are low in mass, like the sun, have that kind of property. They have convection at their surfaces because their surfaces are cold. The reason that they have convection at their surfaces is that their surfaces are cold enough that hydrogen at the surface is not actually ionized. So it has an electron attached to it, and that means that the hydrogen is very opaque to light. And so that drives the convection in the outer surface of the sun.
Right.
When you go up the main sequence, the stars get hotter and hotter at their surface. And when you get to about 10,000 degrees Kelvin, you essentially ionize all of the hydrogen, and you kind of burn away that opacity. And O-type stars have temperatures of like 30,000 degrees Kelvin, so way above the ionization levels of hydrogen. Everything's all ionized up there for the hydrogen. What does this mean? That means that to our understanding up until the last decade, really, it was thought that the outer parts of the O stars were very boring. They would be like the center of the sun, where photons carry all the light, and the plasma is just kind of still and boring and quiescent. Doesn't move at all. Mm-hmm. Now, they're almost like inside-out suns in some ways. The center of these stars actually becomes a churning convection zone. So their cores, the very center where the nuclear fusion is happening, for the O stars, that becomes a convection zone. And that's because there's a lot of movement. And that's because there's so much luminosity, so much brightness from the nuclear fusion happening there that it overwhelms the plasma's ability to carry it. Or it overwhelms the ability of light to carry it through the opaque plasma. And so the cores churn and convect until you get far enough out in the star that the energy has gotten spread out enough by spherical effects, by the fact that it changes with radius squared as you move outwards, that the light can take over and carry the energy. So we thought they had really interesting cores and then these kind of boring outside envelopes. But in the last decade, that story has really changed, and it's led to the outside bits of these stars being far more interesting too.
How so?
So we think that the outside bits of these stars are almost every bit as churning and active, maybe, as the outside of the sun. And the reason for it is similar, but slightly different. So these stars, all the hydrogen has burned away, but you still have some other elements around in them, and in particular, iron. And at temperatures of like 200,000 degrees, iron has this neat little peak in its opacity. At temperatures around 200,000 degrees, iron gets more opaque to light than at either higher temperatures, where you rip more of its electrons off, or at lower temperatures, where the light can't really interact with the iron as well. So in this funny little temperature range around 200,000 degrees, the O stars suddenly become a little bit more opaque to the light. And they're already so very, very, very bright. They're already so close to this thing called the Eddington limit, which is a place where a star is so bright that its own light pushes itself apart against its own gravity, trying to hold itself together. Super sweet. That they actually become unstable to their own radiation pressure, and they start to effectively blow themselves apart. But you go a little bit further out in them and they get cool, because you're going to go from 200,000 Kelvin to 30,000 Kelvin at their surface. And so they kind of blow themselves apart, but then they get cool enough to stop blowing themselves apart and for light to take over. They churn continuously here. So I said we've really learned about this in the last decade. Matteo Cantiello, who I met at the Kavli Institute for Theoretical Physics in Santa Barbara, and who's now at the Simon Center for Computational Astrophysics in New York. Matteo and Jonathan Braithwaite did some just really neat work in about 2011, pointing out that this change in opacity from iron in O stars could really profoundly alter their structure and lead to effectively convection zones at and near their surface.
So to review, what that means is we thought that what we would look at if we got close enough to an O-type star to see one in detail, that you would just see like a bland, diffuse, very, very bright surface instead of the neat, cool giraffe modeled patchy look our star has. And what Ben is saying is because of this opacity in the outer areas, because of this opacity to iron, forcing a convection, that you would go and you'd see, giraffe looking surface.
Or something. We don't actually know.
Or something.
What. So all the O stars are too far away for us to actually get a direct picture of their surface to show us, like, do they have modeled giraffe patterns? What's going on? But what we can do is we can take spectra of them. So the same tool that Annie Jump Cannon was using to classify the stars, we can take spectra, we can split apart their light, and we can look at those dark absorption bands that come from the individual elements. And in addition to telling you the element that's there, the shape of the band also tells you things about the conditions that element is under. And one of the things that we see when we look at the spectral lines from O stars is that for some of the stars, these lines are wide in wavelength space. They're wider than we'd expect from the atomic physics. Mm-hmm. And the way you get that is if you jostle the atoms back and forth a whole bunch so that they're Doppler shifted. And when you look at the width of the lines and you infer how fast the gas would be moving to be Doppler shifted in this way, it's moving at like 20 to 60 kilometers a second, which is very, very, very fast.
Yeah, that's awesome.
And is actually faster than the speed of sound of a plasma at 30,000 Kelvin, which is their surface temperatures. And so these are plasma motions that are faster than the speed of sound can do. But the speed of sound's kind of the fastest you can usually move a fluid around without some special things happening. So it's a really neat question how you even get motions of this sort of speed, but we clearly see evidence for them. It's not a ambiguous fringe finding. It's something we see really strong signatures of.
That's super cool.
One thought about what they might be, these motions we see, is that they may be organized wave motions in the outer atmosphere of the star, driven by that convective zone, the iron bump convection zone that's just a little ways deeper in. So that churning convection is maybe sort of sloshing and moving the material above it and driving large-scale organized wave patterns that are kind of like some of their internal gravity waves probably, that are a bit like the ones you can sometimes see in our stratosphere on Earth, especially in places like here, like Boulder, where we'll get cloud bands above us, where we see regular striping and patternings in the clouds caused by waves propagating through our atmosphere. It might be the crazy O-star ultra extreme version of that.
Does that mean that if we looked at one of these stars, it would be all stripy like a zebra instead of a giraffe?
It might be more like a zebra. It's hard to say because interacting internal gravity waves do all sorts of really cool stuff.
Can I ask, this giraffe metaphor, is that like a Ben Tippett original, or is that a standard way to describe suns?
Yeah. Star, trademark. Ben Tippett.
From my knowledge as a solar physicist, practicing now in various ways since either 2003 or 2009, either when I started or when I got my PhD. I have never before heard of this as a giraffe pattern. And I think that's one of the awesomest analogies I've heard, because it's actually a good description. We may want to narrow in on subspecies. Is it the Maasai giraffe or the
and we can workshop this for you, Ben.
No.
Oh, thank you.
Good metaphors pay off.
I'm going to be a millionaire now. Okay. Do you want to mention sunspots on O's-type stars? Because that story was totally bonkers.
Oh, cool. So here's something that's completely bonkers. Okay, so strong magnetic fields on the sun cause dark regions, sunspots. Okay, so do O stars have strong magnetic fields? Well, it's hard to say. Many O stars, when you look at them, they don't have much magnetic field at all, as far as we can tell. In the light that we see from them. So magnetic fields have an effect in the spectra of stars. And for stars that are far away, it's hard to see things like small spots, like on the sun, but you can see a sense of the global scale magnetic field. For a lot of these stars, you don't see very much field, but for about 10% of them, you see a huge amount of field. And this was actually a study led by some scientists in Canada, the MIMES study, led by, I think, Greg Wade and some others in Canada. MIMES is Magnetism and Mass of Stars. They did a survey of all sorts of massive stars trying to see if they had magnetic fields. And they found some that have wild magnetic fields. So one star that we really enjoy, called Dash 2, has an average field strength of something like 20 kilogauss on the surface of the star. That's crazy. A sunspot's like 1 kilogauss. The average field strength of the sun, even with those sunspots and like smearing it out on the surface, the average field on the sun's like 1 Gauss. This is like 20,000 times stronger, 20 kilogauss.
Wow.
So when you magnetize a massive star, rather than getting a dark spot because you are blocking convection and blocking the heat, well, parts of these outer layers, even with all the waves and stuff, they probably still have light carrying most of the energy. And so in those regions, when you put a really strong magnetic field through it, they become bright spots again. For the same reason we get the bright plage regions on the sun. You get regions where you have a little less gas and you see deeper into the star. And so on the massive stars, like the whole story is flipped around, and you may have these incredibly strong magnetic spots, but they're probably nothing at all like the sunspots we see on the sun. At a trivial level, they're probably bright instead of dark.
Beyond that, they could be completely different.
So, could be completely different in all sorts of other ways. So, okay, one more massive star story. So this star it's one of the strongest magnetic fields we've seen on a main sequence massive star, Dash 2. It was named that in a paper by a scientist named Sundqvist from I think 2013, who did some of these observational studies. Sundqvist and the group of people working with them also studied these how much the Doppler shift you were seeing in these stars,
right.
And in this one very strongly magnetized star, you also see something else extremely peculiar, which is that there is almost no motion at the surface showing up as Doppler shifts in the lines. So the very strong magnetic fields in some of these stars may also be stopping this crazy amount of motion at the surface. And so a super cool question is what's happening when that very strong magnetic field comes down and runs into the crazy strong convection zone of the iron bump that's just a little ways down. This star is like 30 to 40 solar masses too. So it's a big one. It's in the intense range.
I've come to the conclusion that these are pretty cool stars.
No, they're really hot and bright. Weren't you paying attention?
So other cool things about O-type stars. So they are so bright that in addition to like magnetohydrodynamics, which is already pretty cool, the light itself that's trickling its way through them is so bright that it actually couples very, very, very strongly with the plasma. And you have to solve them using something called radiation magnetohydrodynamics, where the light and the plasma kind of interact and churn together in all sorts of ways. And there's been a suggestion that in these very bright stars, especially in these outer iron bump convection zones, that you might get something called photofluidynamics, where you have, this is a phrase coined by a scientist named Ed Spiegel, who's a scientist from Columbia. And Ed Spiegel suggested at one point, and this has never really been explored very well, that the dynamics you might get in the outer convection zones of these stars might be a little bit like the fluid dynamics when you take something like a sand or gravel bed and you force water up through it. Bubbling bed hydrodynamics, a cool laboratory and industrial thing to do. And in this analogy, the light would be like the water, and the plasma would be like the rocks or sand. And in these systems, when you push the water through hard enough, it sort of blows chimneys through the sand that form and collapse continuously. And the sand sort of churns and bubbles away, and the water like trickles through some spots and blasts holes through other spots. And it's this really neat dance between the matter and the light, if this analogy is correct, where you'd have sort of matter in columns falling down and light bursting through columns where you've made the matter thin enough for the light to get through. And that is all happening below the surface of the star, churning away continuously. Yanfei Zhang, a scientist who was at KITP and is now also at the Simon Center, has done some of the first attempts to study these in computer simulations. And I think the jury is still very much out about what is even happening in these neat and crazy stars, even just on their outer surfaces.
It sounds amazing. Would it ever be possible to physically see something like that? Like to record it, to get some visual? It matter, we have to go off what the numbers show.
That's a very good question. For the foreseeable future, it's going to be off of what the numbers show. People have made proposals for ways to make telescopes that could begin to image the surfaces of other stars using interferometry. You'd have to like put telescopes up into space and do all sorts of things that are hard, but not impossible and not inconceivably hard. These are sort of the same techniques that you'd need to take a picture of another Earth-sized world around another star, which people have seriously considered. We're not building one right now, but we kind of know what we need to know to do something like that. And I don't know how close the nearest O-type star is, and so how big of an interferometer you'd need to have to image its surface. But it's not completely out of the question. For now, you'd have to do it based on inference and sort of the signatures you see in other parts of the observational data, like their spectra, like the line widths, what you can tell from stellar structure models, what you can tell from what we see in supernovas, kind of piecing together the story from the less direct evidence. Ryan, one last answer to that question of could we ever see these things? So it's really hard to see them on O-stars because O-stars are so very, very, very far away. In some funny ways, we can actually see some of these processes happening even on our sun, because where the sun's surfaces, where that photosphere is, there's actually more atmosphere above the sun that's just transparent. And we think there have been some early observations of that show some of the same internal gravity waves that I was talking about for the massive stars, but here in the transparent atmosphere of the sun. And we are trying to do new observations of the atmosphere of the sun where you would be able to see these gravity waves and see the convection that's driving them, which is the photosphere, and try and understand the physical processes of how those waves are driven by the convection, which doesn't let you see the process in an O-star directly, but we think that the O-stars may have the same kind of physics as the atmosphere of our sun. The beautiful thing about fluid dynamics is that often you can study one system to understand a different analog system as long as you understand the translation well enough of what's similar and different between the two. And that may even have tie-ins to the excitation of internal gravity waves in our own stratosphere of the Earth from thunderstorms and topography. And so it may even be related to questions of the Earth's climate and how the Earth's atmosphere works.
I do love it whenever we learn something, there's usually applications for it elsewhere that we didn't expect.
A brief note I wanted to make is that when Ben's talking about gravity waves, there's a difference between a gravity wave and a gravitational wave. Gravitational waves are the things like black holes make when they ping together and neutron stars. A gravity wave is essentially when you have a fluid in a gravitational field and you push down on it in one place, that'll raise it up somewhere else, but that causes a difference in pressure because of gravity. Essentially the column height. It wants to all be the same height, so it pushes it down.
That's right.
So like regular water waves on the ocean are gravity waves.
That's cool.
So that's what we're referring to in this case.
That's right.
Well, that was fascinating. Thank you, Ben. Thank you, Hannalore. You've pleased me. Your efforts have borne fruit, and that fruit is sweet. Here is some fruit, Dr. Benjamin Brown. You get a mango.
Oh, how lovely. Nom 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 nom.
And Hannalore Gerling-Dunsmore, you get a star fruit.
Nom nom.
All right. I'd like to thank my guest, Ryan North. Thanks, Ryan.
Thanks for having me.
Yeah, this was fun. Ryan's just finished his run on Squirrel Girl, episode 50.
Yeah.
Yeah, it's fantastic and historic. Hey, everybody. It's time for announcements. First thing, we're going to have a live show in February at the AAAS 2020 General Meeting. Our show is on Sunday, and so if you want to attend, you can get a one-day pass and hear us live. Secondly, as always, we live in an era where podcasts are mainstream, but nobody wants to admit to everybody that they love physics. So, if you know somebody you think might enjoy our show, please tell them about us. That means writing a review online, or it might mean tapping your grandmother on the shoulder and saying, "Hey, Grandma, have you ever wondered how O-stars work? Have a listen to this." We are on iTunes, but also on Stitcher, Google Play Music, Spotify, Pandora, and even YouTube, any way you want to listen to us. The third thing is, as always, I want to announce that if an occasion arises where we need a guest at the last minute, we will take it to social media. We'll be asking on Facebook for volunteers, and if you would like to be a guest on our show asking questions of the physicists like Ryan North did in our particular show, you may. You just need three things. The first is a quiet place where you can record. The second is a very strong internet connection. And the third thing you need is to be available at the time we are recording. Usually it will be a fairly last-minute situation. So if you'd like to do that, please follow us on Facebook or Twitter, and I will send out a call when and if these things happen. Finally, we are still humbly soliciting your donations. Thanks all the donors who have donated to us so far. Your donations go for paying server fees, and for our episode transcription project, and for buying our physicist microphones, and for paying us to go to Seattle in the coming months. So, if you would like to support us, you may send one-time donations through PayPal off of our website, or you can go to the sweet Patreon site and give a recurring $2 or $5 donation. If you give more than $2 and supply your address, I'll eventually send you a postcard. This particular episode of the Titanium Physics Podcast has been sponsored by a collection of generous people. I'd like to thank the generosity of David Holle. I'd also like to thank Raven Bell, Dan Marr, Amir Baniasadi, Cassandra McCarthy, Christoph Beatty, Mr. M.M., the Wild Drew Hickox, the Master Oscar Delgado, Callan Richardson, and Joe Campbell, Ashran Benagiri, J.P. Rotio, Aaron Wheeler, Sander Boros, a Badger, The Sept at Baylor Fane, and Luke Edwards, a Mr. Astro Yuki, Shivang Patel, Mr. Martin Mihulka, Henry Rabung, Peter Scott, Russ Mutsi, Ayush Singh, and Matthew Sullivan, a Daniel Lauzon, Patrick Yeon, Kevin Forsyth, Yer Panem, Hoinam Duong, Stian Henriksen, a TPR Jones, Pascal, a man named Ryan R., and Michael Usher. Senior Canada, Adrian Schoening, Sarah Stradler, Louise Patinella, a guy named Ben, Mr. Matthew Lambert, a fellow named Ayush Singh, David Myrtle, Mr. Ryan Foster, a Janico Freifenberg, Steve Smethurst, Magnus Christensen, Bart Gladys, and Mr. Stuart Pollock, our Emperor Courtney Brooke Davis, Mr. David Lindels, Mr. Carl Lockhart, our eternal friend B.S., and Randy Dalzell, Tina Raudio, the enigmatic Ryan, a gentleman named Crux, and Gabe and Evan Weens, David D., Dan Vale, a Mr. Alex, WTL, Perp Roden, Andrew Waddington, Mr. Jordan Young, John Bleasy, a Brittany Crooks, James Crawford, Mr. Mark Simon, Tucson's Gang of One, Mr. Lawrence Lee, Sixton Linnison, Mr. Simon, Keegan Eade, Andreas from Knoxville, Cadby, Joe Campbell, and Alexander Zani is great, Weena Brett, Eric Dutch, Etienne, a gentleman named Peter Fan, Gareth Eason, Joe Piston, David Johnson, and Anthony Leon, as well as Doug B., Julia, Noah Robertson, Ian and Stu, Mr. Frank, Philip from Austria, and Noisy Mime, Mr. Shlomo Dalal, Melissa Burke, Yassine Urazazi, Spider Rogue, Insanity Orbits, Robin Johnson, Madame Sandra Johnson, Mr. Jacob Wick, Mr. John Keys, and Mr. Victor C., Ryan Kloss, Peter Clipsham, Mr. Robert Halpin, Elizabeth Teresa, Paul Carr, Mr. Ryan Newell, Mr. Adam K., Thomas Charret, Mr. Jacob Est, a gentleman named Brett Evans, a lady named Jill, a gentleman named Greg, thanks Steve, Mr. James Clausen, Mr. Devin North, a gentleman named Scott, Ed Lowlington, Kelly Wienersmith, Jocelyn Reed, Mr. S. Hatcher, Mr. Rob Abrazado, and Mr. Robert Stietka. So that's it for Ti-Fi this time. Remember that if you like listening to scientists talk about science in their own words, there are lots of other lovely shows on our Braculope Media Network. The intro song to our show is Tell Balgary Balgary's Dead by Ted Leo and the Pharmacists, and the end song is Russia by Ramona Falls. Good day, my friends, and until next time, remember to keep science in your hearts.
I visited Russia. I started folding until in one precious doll I had poured in all of Siberia, and I said, love, here ya go. She said, too little too late. Took to the Nile, where I started swimming upstream till I found home. Well, you found the spring growing with God's purest water.